Alright, this video is going to use this. I'm going to use this app to demonstrate the central limit theorem. And the central limit theorem says that if I take a bunch of samples of this distribution up here and then find the average of the averages, like find the mean, if I find a mean, so let me animate this guy here. So I'm going to make this guy 5 and I'm going to make this guy 20, just for grins. So let me animate this. So it's taking 5 random blocks out of here and finding the average and putting them there. And now it's taking 20 blocks out of this group up here. It's going to find the average of these and drop a block there. Now I'm going to animate it again so we can see that one more time. So I'm taking 5 blocks out of this box, put the average there, and then take 20 blocks. I'm going to put the average down here because here I'm finding the mean when there's 20 and here I'm finding the mean when there's 5. All right, so then if I did this like over and over and over again, I can do it 5 at a time. Like there's 5 more and 5 more and 5 more and 5 more. So it says repetitions 22, so I'm doing 5 more and 5 more. You can see that these start to make histograms. Well, I'm going to do something ridiculous. I'm going to do it 100,000 times just to save myself some time. So this is a normal distribution, and this distribution represents the average of all of the sample size, the mean of all of the sample sizes of 5. And you just keep doing that over and over again. And so the mean of sample sizes of 5 is 16, which is the same thing as the mean of the population. Okay? The standard deviation of this group of averages, these are the means of the samples. These are all the means of all the possible samples of 100,000 times. The standard deviation was 5, but the standard deviation of this is 2.23. Well, that's not very close. So let me clear this here. But an interesting thing happens. If I take the standard deviation of my population and I divide it by the square root of the sample size, in this case, which is 5, very interesting thing happens. 2.23, 2.23. Now, if I take the standard deviation of the population, which is 5, and I divide it by the square root of the sample size, in this case it's 20, so 20, I end up with 1.12, 1.18. Okay? So what that's basically called the standard error of the mean. So this is the standard deviation of our samples, and this is the standard deviations of our samples when there's a size of 20. So we can do this a bunch of times, and that same thing will always happen. But what makes this really, really interesting is, what if I was to take this thing and make it skewed? I mean serious skewness. See, I'm gonna skew the crap out of this thing. Let me bring this down here a little bit. So I'm just kind of skew. Okay, I can't skew it any more than that. So we have definitely a skewedness. So even though we know this is not a normal distribution, it's skewed, if I do the same thing with sample sizes of 5 and sample sizes of 20, 100,000 times, I'm just going to cut straight to the chase. Boom, there's my mean and standard deviation. And again, this guy, even though it's seriously skewed, but notice up here, my standard deviation isn't 5 anymore, it's 5.75. So let's check that out. 5.75 divided by the square root of 5, because that's my sample size. Second square root of 5, 2.57, 2.58, was close. How about this one down here? So this is sample size 20, so 5.75, because that's the standard deviation of my population up here that's skewed. And I'm going to divide that by the square root of 20. Hit go. 1.28, 1.28. So what this means is that the central limit theorem tells us that if we know a population standard deviation and a mean of this, or the mean, and notice, oh, by the way, notice the mean of the population is equal to the mean of the sample standard deviations. So these means are the same as the population. That's a big thing about the central limit theorem. And the standard error for the mean is this math stuff I'm doing over here. But we haven't screwed this up enough. So there's a challenge for those. I know there's people out here that love doing stupid stuff like this because you're stuck at home and you're bored. All right, this is not nowhere near normal. Okay, everybody good to go on that one. So I have bimodal thing going on here. The central limit theorem still works. So if I do a sample size of 5 and a sample size of 20 100,000 times, I get these distributions. And notice that the mean of this mess up here is 16.7 and the mean of this guy up here is 16.7. And notice that the standard deviation is 4.09 and the standard deviation up here is 9.12. So let's take 9.12 and divide it by the square root of sample size is 5. So I'm going to put a 5 in there and hit enter. And I get 407 and I get 409. It's really close. Down here, I'm going to take the 9.12, and divide it by the square root of 20, and I'm hoping I end up with 203, and I end up with 203 and some change. So that's real close. And I want to talk a little bit about skewness. This has some skewness, but not very much. In fact, it's negative skewness, which means the ends are fat. If you have positive skewness, it means they're really pointy. And this thing too has negative skewness and has a thing called kurtosis, which is a measure of how skewed this is to how skewed this is. And the reason it's negative is because this is more skewed than that. And notice down here, the kurtosis here is 7%. And so this has some skewness up here, and this is kind of the same. So that's why it's real close to the same. Here it's minus 28%. But don't worry about kurtosis. We can learn it, but it's not good for anything. So here's the challenge. I would like you to play with this and see if you can come up with one that doesn't work. And I want you to notice that here the median is 16, and here it says the median is 17. Notice that these do not target the median anymore. Up until the last one, the median was always the same. I don't know if you noticed that. But is the mean the same? 1672, 1670, 1672. The means are the same. So the mean of this distribution is the same as the mean of these distributions. And that's the fundamental property of the central limit theorem. They're saying that if you sample this thing enough times, you will eventually find the average of this mess up here if you sample it, in groups of 5. Notice that the larger n, the skinnier it gets. Now, unfortunately, we're limited to 25 here. What we're going to do is, in the real world, this n is equal to 30 or more, sometimes 40 or more. So that's what causes you to have a more accurate thing. Notice that this guy is 203, and remember this guy was off a little bit because it's kind of like flattened out when n is equal to 5. All right, so that's the challenge for this. Play around with it, see if you can find a distribution that when you sample all the standard deviations, or sample all the means of all the possible samples, that you end up with a distribution that isn't normal. Of course, it'll always be normal, no matter what this looks like. And the central limit theorem will tell you that the standard error for the mean is always going to be the standard deviation divided by the square root of 20. And we're going to use that property to solve problems here in a few minutes.